Hello students, today we are going to learn about a virtual memory. Virtual memory is a feature of an operating system that enables a computer to be able to compensate shortages of physical memory by transferring pages of data from random access memory to disk storage. This process is done temporarily and is designed to work as a combination of RAM, that is random access memory, and space on the hard disk. Virtual memory is a storage allocation scheme in which secondary memory can be addressed as though it were a part of main memory. The addresses a program may use to reference memory are distinguished from the addresses the memory system uses to identify a physical storage sites, and a program generator addresses are translated automatically to the corresponding machine addresses. The size of virtual storage is limited by the addressing scheme of the computer system, and amount of secondary memory is available not by the actual number of the main storage locations. It is a technique that is implemented using both hardware and software. It maps memory addresses used by a program called virtual addresses into a physical addresses in computer memory. All memory references within a process are logical addresses that are dynamically translated into physical addresses at runtime. This means that a process can be swapped in and out of main memory such that it occupies different places in main memory at different times during the course of execution. A process may be broken into number of pieces, and these pieces need not be continuously located in the main memory during execution. The combination of dynamic runtime address, translation, and use of page or segment table permits this. If these characteristics are present, then it is not necessary that all the pages or segments are present in the main memory during execution. This means that the required pages need to be loaded into memory whenever required. Virtual memory is implemented using demand paging or demand segmentation. Now, what do you mean by a demand paging? The process of loading the page into memory on demand whenever page fault occurs is known as a demand paging. Now, what are the advantages? More process may be maintained in the main memory because we are going to load only some of the pages of any particular process. There is room for more process. This leads to more efficient utilization of the processor because it is more likely that at least one of the more numerous processes will be in the ready state at any particular time. A process may be larger than all of main memory. One of the most fundamental restrictions in programming is lifted. A process larger than the main memory can be executed because of demand paging. The OS itself loads pages of a process in main memory as required. It allows greater multiprogramming levels by using less of the available primary memory for each process. Now, what do you mean by a swapping? Swapping is a process. Out means removing all of its pages from memory or marking them so that they will be removed by the normal page replacement process. Suspending a process ensures that it is not runnable while it is swapped out. At some later time, the system swaps back the process from the secondary storage to main memory. When a process is busy swapping pages in and out, then this situation is called a thrashing. Now, what are the causes of thrashing? High degree of multi-programming. If the number of processes keeps on increasing in the memory, then number of frames allocated to each process will be decreased. So, less number of frames will be available to each process. Due to this, page fault will occur more frequently and more CPU time will be wasted in just swapping in and out of pages, and the utilization will keep on decreasing. Now another cause of thrashing is lacks of frames. If a process has less number of frames, then less pages of that process will be able to reside in memory, and hence more frequent swapping in and out will be required. This may lead to thrashing. Hence, sufficient amount of frames must be allocated to each process in order to prevent thrashing. Now we can see how we can recover a thrashing, that is recovery of thrashing. Do not allow the system to go into the thrashing by instructing the long-term scheduler not to bring the process into memory after the threshold. If the system is already in thrashing, then instruct the mid-term scheduler to suspend some of the processes so that we can recover the system from thrashing.